so exhausted right now. I know it's only 10 in the morning, but whatever. So not sure how useful I'll be today, but we'll see. Over a week ago, yes.
Oh. Not really an asshole. I'm sorry.
That was good. Okay. So since we're getting so close to the end of class meeting time, I don't want to have too much spill over into July, so I'm going to end with an either or thing. So after you finish homework 2, you can either move on to homework 3 or you can do a final. That's an individual choice. So you all can decide how you want to do that. Either one can spill over into July, just because of how long I have to turn in the grades. So please let me know of your choice. For those who don't feel like doing multi-grade homework, and so then things can be scheduled accordingly. So. Okay.
In July, when are you not going to be around anymore? I know we have the conference, and then I think you said you want something.
And I have something a week after that. Yeah, so the middle 2 weeks of July, I won't be here. But otherwise, yeah. Okay, so individually, let me know what do you want to do. I can imagine certain preferences for certain people, but we'll see. Okay, next thing, for homework 2, I need to get some half-decent chalk. Okay, for number 2, so I actually coded it up myself last night and tried to get an idea of what is supposed to happen. And the thing is I just assumed going in that this was meant to be a problem that illustrates the benefits of spectral methods over finite difference. And I'm not seeing that it does, to be honest. It does, especially for a finite difference case, it does show some interesting behavior. So first, I want to talk about the behavior of the exact solution. So we have minus epsilon uxx plus ux is equal to 1. So what happens is, as epsilon gets smaller and smaller, the problem is 10 to the minus 4, but I could have rounded it for different values of epsilon, like 1 or 10 to the minus 2, and then going towards 10 to the minus 4. You have a solution that behaves, now this is on the interval minus 1 to 1. That reminds me, for your solution in the finite difference case, when you define a vector of x's, make sure it's not from 0 to 2, but minus 1 to 1. So what you can do is you could just, if you have a vector of x's that's defined like h times something, like a vector of indices, just add minus 1 to it. So that way it'll start at minus 1 rather than starting at 0. It's not going to throw off your matrix or anything, but just make sure you're dealing with the right domain. And then for the Chebyshev part, if you use it, formula for cosine of pi j over n, you will get points between minus 1 and 1 no matter what. For larger values of epsilon, the solution starts out at 0 and then has a slope of 1, and then it behaves something like this to come back down to 0 at the end. So this is a moderate sized value of epsilon. But as epsilon gets smaller, the function it really wants to behave like f of x equals x plus a constant. So really x x plus 1. So what happens is it comes down more sharply to get back down to 0. So this is a behavior that happens. So as epsilon goes 0, it starts transitioning from that to that. What you might want to do in the process of testing your code, just to make sure you get a reasonable solution, don't use epsilon equal 10 to the minus 4 right away. Use something like epsilon, like maybe 10 to the minus 1 or 10 to the minus 2. Because then you should expect to see, as you increase the number of grid points, something like this. A solution that behaves in a reasonable manner. By the time you get to the epsilon being 10 to the minus 4, it's practically a discontinuity. Like the cliff is really sharp at that point. And what I saw in the computed solution using finite difference is it tries to do this, but you get oscillations, really nasty oscillations. And as you increase the number of grid points, the oscillations situation improves. If you have less oscillation, that's Gibbs phenomenon, essentially. So if you use once you get to 3,000 grid points or so, then it's not so bad. But that epsilon being that small means you need a lot of grid points to get to that. Now the Chebyshev, I really don't like how it's behaving at all, to be honest, because I'm seeing oscillations throughout. And the thing is, I created a differentiation matrix, in the notes, creating the whole thing. And I thought, well, let's try it out. If I give it a function like cosine, does it give me minus sine? It really does. It's so accurate. So that's something it's good to check these things now and then, try to do something simple to make sure that your matrix is correct. So then, if you form a matrix D squared and then chop off the first and last rows. Oh, that reminds me. The whole matrix D is singular, like I mentioned when you asked me about it, and therefore D squared is singular. But once you chop off the first and last rows and columns, it's not. Generally, we have Dirichlet boundary conditions, even though differentiation is a singular operation. Once you deal with only interior points, the matrix you get is supposed to be non-singular. It may still be badly conditioned, but you can still get a unique solution. So, and actually, if I go ahead and try out my spectral code, but with a not so small value of epsilon, okay, I check my number of grid points. Well, 100 grid points, and actually, well, even with epsilon being 10 to the minus 2, it's still pretty steep, not as steep. Whereas if I try 10 to the minus 1, okay, then less so. So in fact, you probably only get something like this with epsilon equal 1. Because even I just did epsilon 10 to the minus 1 just now, and it looks like that. And then 10 to the minus 2, it like that, pretty much. It's very close to vertical. So not surprising that with 10 to the minus 4, that you get that behavior. So now if I try fewer points, hardly any points at all, 10, well, it's still, for 10 points, does a pretty good job. This is with a larger value of epsilon. But then as soon as I jack it up to 10 to the minus 4, all hell breaks loose. So that's unfortunate. Because I was thinking, oh, this problem should be a nice advertisement for here's how great spectral methods are when finite difference methods fail. It's not that. So pretty disappointed right now. Okay, so does anyone have any particular questions about? Yeah.
I just want to make sure to check my edge with you. Is it 2 over n plus 1?
Yes, it is. for finite difference, yeah.
And then x is minus h to h.
Um,
We want it to be minus 1 to 1.
well, yeah. Well, here's how you could find it. Like, so if h is 2 over n plus 1. So if you want a vector x that has all the points, including boundary points, you could do like minus 1 plus h times 0 to n plus 1. I'm putting a transpose in there to force it to be a column vector. So that way, when the index is 0, you just get minus 1. And when the index is equal to n plus 1, that n plus 1 would cancel with this n plus 1 to give you minus 1 plus 2 is 1. But for in the finite difference case, the only time that really comes into play, the x, is when you plot. And it just affects what your horizontal axis points are. Your solution's not going to be affected. And then for the Chebyshev case, and you're using cosine pi j over n. So if you let j go from 1 to n minus 1, that's the interior points. But if you let it go from 0 to n, then you get the boundary points too. But you need all the points just to make the matrix, because you're making all of D, so then you can square it, and then chop out the first and last rows and columns. The other thing that was kind of screwy, and I want to try it again, for the Chebyshev case, if I use a lot of points, oh, yeah, even at 1,000 points, it, what happened was it gave me a bad matrix. It said, like, yeah, okay, yeah, close to singular or badly scaled, when it's supposed to be non-singular. Now, if I try something else here, well, oh, I actually made D in 2 different ways. Like, there's one formula in the notes that uses Chebyshev directly, but the other uses Lagrange polynomials. If you produce the same matrix. Okay, this is interesting. Oh. All right, I'm going to try this again with lesser grid points. Let's say like 100. Okay. Whereas if I try finite difference with the same numbers of points, like 99, awful oscillations, but then if I go up to 999, okay. So I found an instance in which spectral methods are better. If you run both methods with about 1,000 points, so like exactly 1,000 for Chebyshev and 999 for n equal 999 for finite difference, but it doesn't really matter. The point is the neighborhood of 1,000 points. The Chebyshev solution looks really good. It's like this, only sharper because of the small value of epsilon. But there's no bad behavior. Whereas the same number of points for finite difference, it behaves well up to this point, and then you get these screwy oscillations at the end due to the Gibbs phenomenon. So even though but then what's strange is for a smaller number of points, finite difference solution, you have these wild oscillations towards the right end. Whereas with Chebyshev, you get oscillations all over the place in the whole solution, which is like, okay, that's awful. But again, if both solutions are awful, then they're just awful in different ways. Chebyshev seems to get to a good solution sooner than finite difference does. Okay. So that's one interesting thing to watch out for, to make sure that you're getting the correct behavior. In fact, as I choose more and more points of finite difference, like of the 3,000, the oscillations get pushed more towards the right end, but they don't go away. Whereas with Chebyshev, they do go away. So, okay, so that's something. Okay. So in fact, because what happens is it's kind of interesting that finite difference exhibits the kind of behavior that you observe in Fourier series when they're trying to deal with a non-periodic function, even though this finite difference approximation really has nothing to do with that. So that's interesting. But it's kind of like what I've seen in research, for example, using certain time-stepping methods of finite difference matrices. That if your initial data has some discontinuities, your solution's supposed to be smooth, but you still see these high-frequency oscillations. Okay, so now you know what to watch out for to make sure that your solution is correct or not. And so I'm still not happy about the fact that for a smaller number of points, the Chebyshev solution is full of oscillations. I still think that's pretty bad, but at least in the long run, Chebyshev wins. So, okay, so any other homework?
So I got even those oscillations for the other method.
Which other meaning what?
For finite difference.
Yeah.
With a smaller, and I got those oscillations. But once I put 1,000, then it was kind of.
Can you show me? Yeah, because it's what happens is all the bad behavior it's getting pushed to the right. You see less of it, and it's not as extreme. It's not something that you see go away completely. Yeah. Okay, so see, that's still bad. It's not as bad. And what will happen is, because the solution is supposed to go from y equals 0 up to y equal 2 thereabouts, and then come back down. But then the oscillations take you up to 4 or so, and then as you increase the number of grid points even further, I'm at 3,200 grid points, and the oscillations go up to 3.5. And so as you increase it further, it would become less and less. But you need so many grid points to get a reasonably accurate solution. So you're better off from Chebyshev. But the one thing if you look at the as far as the formulas for Chebyshev, there's two ways of doing it that are given in the notes. So the one that has this block structure, where you have these formulas. I'm not going to get it exactly right, but this sort of thing. That's Chebyshev specific. That's the one you should use. So the formulas up above, so use these guys. The formulas up above that in the notes that have AI over AJ, XI minus XJ. I tried that too, just to act as a check on my formulas. And for small number of grid points, that's perfectly fine. But for these formulas, don't use those. Because you get, even at a value 1,000 grid points, for that, there's too much round-off error in those formulas, and you get something that is terribly conditioned. Whereas this matrix, even if you use, I'm using up to 3,000 points, and it's fine. So, but this happens a lot, right? To be careful what formulas you use, even if they're mathematically equivalent. That's still a problem. All right. Any other homework 2 questions? Okay. So, how many of you are currently working on problem 5? Okay. And everybody else is mired in problem 4 or earlier. Okay. All right. Just so I know where people are at. What I'll spend some time on tomorrow is like a preemptive help with homework 3. So get an idea of like what the problem's really asking about and what I have in mind for you guys to do with that one. Because basically it's 2 problems. One of them is one-dimensional, the other is 2-dimensional, dealing with multigrid. And implementing certain iterative methods, or maybe using some functions for iterative methods that are already in MATLAB. Like you would not implement a constant gradient yourself, but you would use MATLAB's function for it, PCG, for comparison purposes. But the basic multigrid algorithm, like solving the system, then computing a residual, dealing with that, of course, a grid. And when I say solving a system, not using backslash, but using some sort of smoother, like Jacobi or Gauss-Seidel or something like that, and how we can go ahead and implement that. I'll look at the problems again. Due to the dwindling amount of time we have, I might cut some things out, but we'll see. Okay, so that's something I'll talk about tomorrow. Okay.
Excuse me, tomorrow you're going to talk about exam also?
Oh, yeah, that's something. I'd like to get a feel for how many are going to do that as opposed to homework 3. So, not to pressure you guys, but the sooner you can express your preferences to me, the better it'll work. Okay. The main thing I can say for now about oral exam is I'm basically going to be looking at the notes to just figure out what I want to ask. Mainly on higher level concepts, like why would someone use a spectral method compared to a finite difference method? Like what are advantages and disadvantages of one approach over another? Comparison of iterative methods versus direct methods versus what's the benefit of multigrid? Okay. Which way?
Towards an oral exam.
Oh, okay. All right. Well, but the thing is, different people have appetites for different things. So, I mean, I might be changing someone else's mind the other way for all I know. So, Lax equivalence theorem. Definitely going to ask something about that. What are the various things in it mean? What understanding concepts of local truncation error or global error, that sort of thing. It's not really practical to say, okay, go to a board and write some code for maybe tiny snippets of things, but yeah. So, but really, it's stuff in the notes that I'm going to look at. Okay, so you just let me know whenever, or should we email a message or something if you have your preference, and then that will help me plan how to spend time for the rest of the week. Okay. Now, the funny thing is, like, the only stuff I have left to cover, well, it's important stuff because it deals with time-dependent problems. We've been doing only time-independent problems, but you're not going to get any homework on this because I just don't have problems for that. Okay. time-dependent problems are the ones that I personally am most interested in. So we're interested in problems of this form, like du dt is equal to lu, where L is some operator, or it could be utt, so we're not limited to first derivatives in time, although that's where our main focus will be. On some domain omega, and some interval in time, so starting at time 0 and going towards some final time. And then we have the initial condition. And then we have a boundary condition. In this case, Dirichlet, well, of course, it could be something else, like Neumann or periodics. This is for x on the boundary. On the boundary of omega, so that's our boundary condition. So all of these put together make what is called an IBVP, initial boundary value problem, because we've seen initial value problems, we've seen boundary value problems. Here we put the two together. Okay. And some examples of L of interest. Well, we've seen plenty of Laplacian. So that would lead to the heat equation if it's du dt on the left side, or the wave equation, in which case it's utt. And if it's a wave equation, you need a second initial condition on du dt equal to some function. Just like with second order ODEs, like it's on 285, you needed two initial conditions for that. You might also see L is equal to some vector dot product with the gradient. So that happens with advection equations. Also, the Laplacian squared. This is a biharmonic. Not sure where I got cut off, but so just different examples of L. Laplacian for a heater wave equation, depending on your time derivative. Vector dot product gradient for advection equations, or Laplacian squared gives you that's a biharmonic. You pair that with UTT and you get the beam equation. Actually, I remember the time independent equation involving the Laplacian squared. That's a biharmonic equation. Megan Richardson. And then here it cuts out in a couple minutes. Okay, so at least I saw it cut out. Megan Richardson worked on the biharmonic equation, time-independent equation. So like Laplace's equation, except Laplacian squared, for her master's thesis. That's the problem that Dr. Tian was interested in. And then one more is some function f times the magnitude of a gradient, because a gradient is a vector. When it's a time-independent equation, so there's no time derivative, like you just set it equal to some value. It's called the Eikonal equation. It's totally nonlinear. But with a time derivative, you get an equation that's called the level set equation. Level set equation is used a lot in actually for computer graphics to model changing interfaces between substances like air and water or air and fire. So it's used for a lot in animations. So things I wish I could spend time on if we had more than 4 weeks. Okay. And if you let du dt equals 0, then what you have is a steady state solution. And so these equations reduce to things like Laplace's equation or Poisson's equation. So the equations we've been studying up to this point are really like steady state versions of these equations. Okay. these kind of equations numerically. There's different approaches, but there's really one kind of approach that I'll focus on. And so going forward, I'm just going to work with a first-time derivative. Just some make the discussion simpler. So because we have to discretize in time and space. Okay. So the approach that we're going to look at is that's most often used is you have some PDE, so general form like before, du dt equals LU, and you discretize only in space. So that gives you a you get a matrix A, just like the matrices that we've been seeing, like when you're using finite difference or Chebyshev or whatever. And you get a system of ODEs. So now you have a separate ODE for each component of your solution U. That's now vector values at each of the x's. And this is called the method of lines. Because now your unknowns are values of your solution at particular x's. So along each line in your space-time domain corresponding to a certain x value, you have an ODE for a certain unknown. But all these ODEs are coupled together because of the spatial derivatives that you have. So now we need to look at how do you solve ODEs. Now this is something that you would have seen in other classes. It's covered in 561 and 772. So all of you have taken at least one of those. And that's what we're going to look at here. So now the thing is, sometimes what people do is they actually discretize in time first and then in space. But we're not going to really get into that. So we're just going to focus on, we assume that you've discretized in space already to get to this point, because we know how to do that. And now, how do you solve a resulting system of ODEs? All right, so ODEs, and throughout, I'm going to assume we actually have a system of ODEs, or it could be one ODE, but I'm going to keep the discussion as general as possible. So we have y prime is equal to f of t and y, where y is a vector function of t, and f is a vector value function of t and y. And then you have some initial condition, y0 is some given vector, y not. So whether y is a vector or scalar doesn't really affect how I discuss solution methods. Okay. So what we do is we perform time stepping. So we approximate our exact solution, y of t, at times t sub n, which would be n delta t. So we choose some time step delta t, and so we're going to approximate a solution not as a function of t, but as certain times, t1, t2, t3, and so on. I'm going to assume, okay, so this is our time step. I'm going to assume that we keep the time step uniform, but there are methods for changing the time step. This is something that Haley's working on, actually, adaptive time stepping. So we're not going to get that far, but just letting you know that those are out there. Okay, so I'm going to show you the simplest time-stepping methods based on the simplest ways of approximating a derivative. Now for du dt instead of du dx. So if we use a forward difference in time applied to this ODE, what we get is first some notation. I'm going to let y n, so superscript n, is an approximation to the exact solution y at t sub n. So whenever you see this, I'm referring to what your numerical method computes, as opposed to what we're actually hoping for to get exactly. So, so for forward difference, I approximate the ODE by the exact solution at time n plus 1 y tn over delta t is approximately f at time tn. So all I've done there is just approximated the derivative with respect to t at time tn by a forward difference. So now what I can do is rearrange this, and instead of using the exact solution, it'll be the numerical solution. So yn plus 1, if I solve for that, is equal to yn plus delta t f of tn yn. And f is a vector value function. Okay, so that's our simplest time-stepping method, which is called explicit Euler, also known as forward or Euler, or sometimes just known as just plain old Euler's method, when there's no possibility for confusion, but I'm about to talk about another one. Okay. So everything starts from here. Basically, the other time-stepping methods are attempts to improve on this one, and it's not hard to improve because it's actually not a very good method, but simple to implement. If you're okay with taking a zillion time steps in a really small delta t, then knock yourself out. Okay. So that's when we use a forward difference. But suppose I use a backward difference. At time tn plus 1 rather than tn. So, so I have y of tn plus 1 minus y of tn over delta t. Now, it looks exactly the same as what I had before. Well, actually, it is. But the use of it is different because instead of approximating the time derivative at time tn with a forward difference, it's actually with approximating the derivative at time tn plus 1 using a backward difference. So this is f of tn plus 1 y of tn plus 1. And then rearranging we get yn plus 1 is equal to yn plus delta t f of tn plus 1 yn plus 1. Now, it looks exactly the same as explicit Euler, except f is evaluated at time n plus 1 rather than time n. So this is called implicit, also known as backward Euler. Okay. So, and the thing is, yn plus 1 appears on both sides of the equation. So now, if f is a really simple function, like a linear function, you can go ahead and solve a simple equation for yn plus 1. But you have to solve some equation for yn plus 1, but it could be like a nonlinear equation. So because of this, you have to solve some sort of an equation. If it's a linear ODE, or system of ODEs, you'd be like inverting a matrix. But if it's not linear, you have to use some iteration, like Newton's method or secant or something like that, or like some sort of fixed point iteration, which is really what this satisfies. So that's more work per time step, but as we'll see later, there's still actually substantial benefits to using implicit methods like this one rather than explicit. Okay. Actually, I'm going to go ahead and call for a break now.
You know, they're AC forever. Just read my meter. Yeah. Just read it to them so they would charge me.
Okay, we're recording, by the way.
Sorry.
Okay, all right. So now we've seen the simplest time-stepping methods, implicit and explicit Euler. We have similar concepts for error as before. Local truncation error is informally defined the exact same way. You plug the exact solution into your numerical method and see what's left over. The only difference is if you just take explicit Euler, implicit Euler as I've written them, like yn plus 1 equals something, and you plug the exact solution into that, you have to, bless you, you need to divide by delta t. Now the MIT notes actually doesn't do that, but everybody else does, so I'm going to keep with that. So for explicit Euler, what you get is, I'll use the same notation as before. So tau n, the local truncation error at time tn, is so the exact solution at time tn plus 1 minus the exact solution at time tn over delta t minus f at tn y at tn. So, okay, so if anyone watches these videos, it's like, wow, he repeats himself a lot. I can't be sure. So that way you can actually see the approximation of dy dt easily. So now that we have this, so in general, this is how you rearrange the method to define local truncation error. And then what you do is use Taylor expansion. Actually, I just jumped to the punchline in the notes, but so you expand around Tn. So you're expanding this, y of Tn plus 1, and you get y of Tn plus 1 is equal to y of Tn plus y prime, plus delta t, which is Tn plus 1 minus Tn, y prime of Tn. And then I'll just go on one term more, plus 1/2 delta t squared y double prime at some unknown point c. So this is the Taylor expansion of y of Tn plus 1 minus y of Tn all over delta t minus f. Okay. And then we simplify as much as we can. So the y of tn terms cancel out. And then, this is the exact solution. Y prime equals f evaluated at the same time. So this term, this is delta t over delta t will cancel too. This cancels with this. So the only thing left is this term over delta t. So one of the delta t's cancels out. And you're left with delta t over 2 y double prime at some unknown point. So that is the local truncation error for explicit Euler. And the unknown point c is between Tn and T plus 1, Tn plus 1 by Taylor's theorem. Okay. So what we see is, because there's a delta t not raised to any power, the local error is first order in time. And can't really expect anything better with such a unsophisticated method. Okay, so that's local truncation error. But what we really care about is the global truncation error, so GTE. Of course, when I think GTE, I think the awful phone company, but I don't know if they exist anymore. Okay.
You mean Z?
Oh, GTE.
I've heard Z.
Okay, I haven't heard of them, but I had GTE out in California once. That was a very long time ago. Okay, so global truncation error, also defined in a consistent manner as for time-independent problems. So I'll just call that E n is equal to the exact solution at time tn minus the approximation. So of course we want that to be small, and we want it to go to 0 as delta t goes to 0. So here's what we can do to figure out global truncation error. We can express the error at time n plus 1 in terms of the error at time n. So if I write out what the exact solution satisfies, y y of tn plus delta t f at tn y of tn plus local truncation error. So this is just a rearrangement of the equation I have over there that defines the local truncation error. But now I have it written like explicit Euler is, because I want to compare them. So explicit Euler itself is yn plus 1 is yn plus delta t f of tn yn. Okay. So now what I can do is subtract these. So on the left side, I'll just have en plus 1. These terms I'll have en. And then I have delta t times a difference of f values. And I'd like to be able to simplify that to bring in en into the picture, but I can't do it yet when I have a local truncation error term. Now, before I go any further, I'm going to make an assumption about f. We assume f is Lipschitz continuous. And that means that Lipschitz continuous in the y variable. So we evaluate f twice at the same time, same t value but different y values. So f of t y2 minus f of t y1. Now, f is a vector valued function, so we're taking some vector norm here, or if we only had a single equation, it would just be absolute value, is less than or equal to some constant L, which is called a Lipschitz constant, times the difference in the norm of y values. Okay. All right. So, okay. So this is what's going to allow me to get around the fact that I have two evaluations of a nonlinear function that normally I could not simplify. But I don't care about computing the error exactly. I mean, that'd be great if I could, but just coming up with an upper bound on it, that's what we really need. Or that's all we can hope to get. Okay. So now what I'm going to do is take norms of both sides. So we'll have norm of en plus 1 less or equal to norm of everything else on the left side, but I'm just going to go ahead and use a triangle inequality, that the norm of a sum is less or equal to the sum of the norms. So I have norm en plus delta t, and here I use the Lipschitz criteria on f, so I have that f difference in f values is less or equal to L times the difference in y values, but that is en again. And then plus the norm of, well, still delta t. Oh, wait a minute. Ah, dang it. I goofed. When I rearranged the definition of local truncation error over here, this needs to have a delta t in front of it. And that's in my notes, I just forgot to copy it down. Okay. So make sure you have that in there. So that's really weird. When I was watching on my screen here. At first, like, it was really dark, and then as soon as I started walking towards it, it lightened up again. So I'm not sure what that's going to mean for the video, but as uploaded. Okay, so that's why there's a delta t over here times the norm of the local truncation error. So this just comes about from the Lipschitz applying the Lipschitz condition. That's what brings the L into the picture. And then that norm of y2 minus y1 is the norm of this difference, but that by definition is en. So I can simplify this a little bit. So this is 1 plus delta t L en plus this extra term. Okay. Now, what I'm going to do now is, because now I have a recurrence relation. I have a bound on en plus 1 in terms of a bound on en. So what I can do is I can apply this recurrence as many times as I want. So I'm going to apply the same relationship to this en here. This is less than or equal to, okay. So now I'm going to expand it one more time and then multiply everything out, and then hopefully the pattern will become apparent. So, well, okay, so I have 1 plus delta t L squared, and then I have en minus 1, which I'm now going to write as 1 plus delta t L en minus 2 plus delta t tau n minus 2. And then the other terms I had from this, I still need to write down. So that's going to be plus delta t 1 plus delta t L tau n minus 1 plus delta t tau n. Okay. So now, let's see. If I let's see if I expand out everything, I get 1 plus delta t L cubed e n minus 2 plus delta t times a whole bunch of stuff. That's going to be 1 plus delta t L squared tau n minus 2 plus 1 plus delta t L to the first power tau n minus 1 plus delta plus nothing at all times norm of tau n. Okay. So what we have here is, notice in each term we have an earlier local truncation error, but it's multiplied by increasing powers of delta 1 plus delta TL. So now what I can do is, if I were to take this all the way back to E0, so I'll be using an inductive argument to prove this. The norm of En is less than or equal to 1 plus delta T L to the n times E0 plus delta T times a sum from 0 to n minus 1 of 1 plus delta T L to the I times tau n minus I. Because notice, if you look at the power of 1 plus delta TL times the superscript of tau here, in this case, and this case, they all always add up to n. So that's what I have going on down here. Okay. Now, but then what I'm going to do is I'm going to get rid of this, because at time 0, you have the exact solution. It's the initial data. So that's 0. That's fine. And then what I'm going to do is, well, this local truncation error for explicit Euler, we know what this is, kind of. That is equal to delta t over 2 times the second derivative of y at some unknown point. So before I go any further, I would like to be able to factor this out. And I have a less than or equal to. So I'm going to let capital M be the maximum of the norm of y double prime of t going from 0 to capital T, my final time. Okay. So that way, I can just say that this, so that would tell me that any local truncation error is, well, the norm of it is less than or equal to delta T m over 2. So by bounding that independently of I can factor it out of the sum. Okay, so now things are starting to get simpler, and they're going to get a whole lot simpler still. So what I currently have is log of n less than or equal to, so that first term, that's gone. So now I have delta t squared m over 2, because I had a delta t already, and I factored out the local truncation error upper bound. And then I have a sum of 1 plus delta t L to the I. Now, this is a geometric progression, and there's a nice formula for the sum of a finite geometric progression. So this is exactly equal to, so I'm summing powers from 0 up to n minus 1. So this gives me 1 plus delta t L to the n minus 1 all over what's being raised to that power, minus 1. I don't know if it rings a bell with anybody. It's one of those good to know things. But that in general, 1 plus r squared plus r cubed up to r to the n is equal to r to the n plus 1 minus 1 over r minus 1. Comes in handy for a lot of things. Okay. So now I can simplify down below. These ones cancel out. So what's left down here is just delta t, which cancels with one of the delta t's up here. So now I have delta t m over 2, and then I have 1 plus delta t L to the n minus 1. Now, 1 plus delta t L. Those are the first terms in the Taylor series. So this is of e to the L delta t. So I can include that in my upper bound. And so I can say it's lower bound because everything in here is positive. So I have delta t m over 2, and I have e to the L delta t n, but delta t times n is, that's your final time, because you're taking your time interval, or at least as an upper bound. So this is L capital T, because I want to get delta t out of the picture, minus 1. So really what happened is n is less than or equal to the length of a time interval you're stepping through, because going from 0 to capital T divided by delta t. So capital T over delta t is a total number of time steps you're going to take. So little n is going to be less than or equal to that. So that means that e to the L delta t times n is less than or equal to e to the L delta t times, I'll call this fraction n max, but this is equal to e to the L capital T. So that's really what happened to go from here to here. So as a result, this is the best bound, simplest bound we can get for the global truncation error. But we see that there's a factor of delta t in here, so we proved first order accuracy for explicit Euler, because everything else is independent of delta t. So as delta t goes to 0, this whole thing's going to go to 0. This is actually a terribly crude upper bound on the error. Like if I try to use this error bound to figure out, like if I want a certain accuracy in my solution, and I set delta t based on this, what I would find is I'll actually get way more accuracy than that. But at least it's a way to prove once and for all that this is, what we've shown is explicit Euler is convergent. Right. So when the local truncation error goes to 0, the method is consistent. When the global truncation error goes to 0, the method is convergent, which is what we really want. Now, the MIT notes, they define local truncation a little differently. They say that what for explicit Euler is delta t squared. But that's why most people, including myself, we divide by delta t in the local truncation error. So that way the local truncation error and the global truncation error have the same order. So local error, global error for explicit Euler, first order. And both explicit and implicit Euler are examples of what's called a one-step method. And so this proof for explicit Euler's convergence can be used to show convergence of any one-step method, provided that the way you approximate the time derivative is Lipschitz continuous. So for a general one-step method, yn plus 1 is equal to yn plus delta t times some function phi that depends on tn, yn, and your time step. So this is how a general one-step method can be described. So for instance, in the case of explicit Euler, your function phi is just equal to f, exactly. I think actually, I got this out of one of the other textbooks, Burden and Fairs. But for an implicit method, actually, this would require yn plus 1 rather than yn. So the method is consistent if you plug in delta t equals 0, then you get f. Well, in the case of explicit Euler, phi is f, so that's not a problem. So consistency follows easily. The method is stable if your function phi is Lipschitz continuous. In your y variable. Now, in the case of explicit Euler, phi is f, so all you need is for f to be Lipschitz continuous, and you're good to go. But for a different one-step method, you have more work to do to show that whatever function phi that's approximating your time derivative is also Lipschitz continuous. If the method is consistent and stable, then it is convergent. So this proof that I did for explicit Euler can be generalized to any one-step method of this form, where the L is your Lipschitz constant for your function phi to give you stability. And because of a local truncation error going to 0 by consistency, and then an existence of this Lipschitz constant L for stability, all of this proof works out exactly the same way as this, and you show convergence. And you always get that the global truncation error is the same order as the local truncation error. Okay. Now, unfortunately, I only have 4 minutes left. And what I have next is not going to be 4 minutes. Okay, so I'll stop here. So higher order methods, these are first order. Higher order methods, I'll talk about tomorrow. When you can, again, I don't want to impose pressure or anything, but just as a convenience, the sooner you can let me know of your preference for multi-grid or final.
Could you spend the next 4 minutes talking maybe more about what the final would be? I know you said some things already.
Okay, let's see. If I were to look at the notes, well, okay, for one thing, the first part of a course where I spent talking about is kind of like a 606 review about more analytical properties of PDEs. I'm not going to ask anything about that whatsoever. So you can forget about that entirely.
You said something about advantages and disadvantages of different methods.
Yeah, like a comparison of, like, for instance, finite difference versus spectral.
Okay.
in terms of what kind of problems are we best suited for, how well do they work, consistency, stability, convergence. What do they all mean? So now I've talked about those concepts already for time-independent problems. I'm in the middle of them for time-dependent problems. I'm going to talk, as I get to the very end, I'll talk more about stability. Let's see.
So this stuff would be on file.
Yes, but at least it'll be fresh in your mind. Okay. Okay, I'm looking at the notes. See what else I can say. All right. So in other words, the notes have a total of 5 chapters, but chapter 1 you can forget about. Okay. So I'm looking at finding difference. What is a stencil? What's the general approach to how you come up with a stencil? I'm not going to make you solve a system of equations at the board, but certain examples that we've seen are good to keep in mind, like forward difference, center difference, backward difference. How accurate are they? Why would I use a center difference over a forward difference? Because they both involve the same amount of work. They both have 2 points. This is for a first derivative. Okay. How do I handle a boundary condition? Like a Dirichlet boundary condition, for instance. Things. Also, even though I looked to my notes for inspirational questions, I imagine I could focus more on things that you've had to actually work with on the homework, certain tasks you had to do there, because I figured that'd be fresher in your mind. Okay. What is the Lax equivalence theorem? Okay. Looking at spectral methods, we have Fourier versus Chebyshev. When would you use them? And what we saw is in both cases we have constructing differentiation matrices. No, I'm not going to ask you what the entries are, but we saw other approaches to carrying out differentiation for both kinds of spectral methods, Fourier versus Chebyshev. So what's the advantage of one over the other? A finite difference matrix is sparse. Most ones we saw were tridiagonal, whereas differentiation matrices for spectral methods are not. So why would we use spectral methods? And there is a good reason that I went over. Okay. What's Gibbs phenomenon? If we have a differentiation matrix for 1 dimension, how do we go to 2 dimensions or 3 dimensions? Okay. What are the issues involved with certain types of systems methods for AX equals B? There are 3 categories: direct, stationary iterative, or Credo subspace. Why do we have preconditioning? Okay, so hopefully that's not going to go on. Okay. All right. Okay. Well, I've used up 4 minutes, so actually we've gone a little bit past that. So, okay.